Picture this, a vast empty canvas, darker than the darkest night you can imagine. There are no stars, no planets, not even space or time as we know it. This is the canvas upon which our universe's story will be painted, a story that begins with a bang. It's a story of cosmic evolution, a grand symphony of matter and energy, gravity and light. Our journey begins with the Big Bang, an event so monumental it defies our everyday understanding. It's not an explosion in the traditional sense, like a firework going off in the night sky. Instead, imagine the fabric of space itself, expanding rapidly from an infinitesimally small point. Everything that is, was, and ever will be was compressed into this point, a cosmic seed. As the universe expanded and cooled, energy transformed into matter, following Einstein's elegant equation E=mc². The early universe was a chaotic soup of particles, a cosmic ballet of creation and annihilation, but gradually, order began to emerge from the chaos. The universe continued to cool, and the fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, took hold. These forces, like cosmic architects, began to shape the universe as we know it. Gravity pulled matter together, while electromagnetism governed the interactions between charged particles. The stage was set for the grand saga of star formation, the birth of galaxies, and ultimately the creation of our solar system and our home planet, Earth. The Big Bang wasn't your typical explosion. It was the expansion of space itself, stretching the very fabric of the cosmos. Imagine dots on a balloon as it inflates. The dots get pushed further apart. This is how galaxies recede, not by their own motion, but by the universe's expansion. In the first moments, the universe was an inferno, a seething cauldron of unimaginable heat and density. As it expanded and cooled, particles combined, forming protons and neutrons. Eventually, electrons were captured by nuclei, forming the first atoms. This event, known as recombination, made the universe transparent to light. The afterglow of the Big Bang is still detectable today as the cosmic microwave background radiation. The early universe was a vast expanse of hydrogen and helium gas. Tiny fluctuations, amplified by gravity, became the seeds of galaxies, stars, and planets. These fluctuations eventually formed the cosmic structures we see today. Within the vast expanse of the early universe, gravity began to exert its inexorable pull. Regions of slightly higher density attracted more and more matter, growing denser and hotter over time. These collapsing clouds of gas and dust became the cradles of star formation, stellar nurseries where the raw materials of the cosmos were forged into brilliant, shining stars. Imagine a giant cosmic cloud of gas and dust, swirling and contracting under its own gravity. As the cloud collapses, it spins faster and faster, like a figure skater pulling in their arms. The center of the cloud heats up tremendously, reaching temperatures and pressures high enough to ignite nuclear fusion, the process that powers stars. Inside these stellar furnaces, hydrogen atoms are fused together under immense pressure and heat, creating helium and releasing a tremendous amount of energy. This energy, radiating outward from the star's core, counteracts the inward pull of gravity, achieving a delicate balance that allows the star to shine for millions, even billions of years. These first stars, massive and short-lived, were crucial for enriching the universe with elements heavier than hydrogen and helium, the very elements that make up planets and ultimately life itself. As these stars reached the end of their lives, they exploded as supernovae, scattering their newly formed elements far and wide. This cosmic recycling process enriched the interstellar medium, seeding the universe with the ingredients necessary for the next generation of stars and planetary systems, including our own. Within the vast, dark expanse of the early universe, enormous clouds of hydrogen and helium gas, sprinkled with the remnants of exploded stars, drifted like cosmic tumbleweeds. These clouds, vast beyond imagination, served as stellar nurseries, the birthplaces of countless stars, each a radiant beacon in the cosmic expanse. Deep within these collapsing fragments, gravity's relentless squeeze ignited nuclear fusion, transforming cold, dark clouds into brilliant, shining stars. Section 2, the cosmic dance of fusion. A star is born. As the core of a collapsing cloud fragment contracted under its own gravity, the temperature and pressure at its center soared. Imagine billions of tons of material squeezed into a space smaller than our solar system. This intense pressure and heat created a swirling sea of charged particles called plasma. At temperatures exceeding 10 million degrees Celsius, nuclear fusion began. Hydrogen atoms fused, releasing an incredible amount of energy. This energy flooded the stellar core with light and heat. The energy created an outward pressure. It counterbalanced the inward crush of gravity. This equilibrium defined the life of a star. As long as the star had hydrogen fuel, it shone brightly for millions of years. The birth of a star was not silent. Intense radiation blasted away the surrounding gas and dust. A stellar newborn, radiating energy, joined the grand symphony of stars. Section 3. Stellar evolution from newborn star to cosmic dust. A star's life cycle is determined by its initial mass. Massive stars live fast and die young, ending in spectacular supernovae. Smaller stars like our Sun burn steadily for billions of years. Eventually, all stars exhaust their fuel and transform, dispersing cosmic dust. Section 4. Supernovae. The spectacular demise of stars. For massive stars, the end of their life cycle is a truly spectacular event, a supernova. Imagine a star many times larger than our Sun, suddenly increasing in brightness, outshining an entire galaxy. This brilliant outburst marks the star's final act, scattering its stellar guts across the cosmos. As a massive star exhausts its nuclear fuel, its core collapses under its own gravity. This collapse triggers a shockwave that rips through the star's outer layers, blasting them into space. The energy released during a supernova is staggering, briefly outshining billions of stars. For a short period, a single supernova can outshine its entire host galaxy. Supernovae are essential for the evolution of the universe. The intense heat and pressure forge heavy elements, such as gold, platinum, and uranium, elements heavier than iron that cannot be created within the normal fusion processes of stars. These elements enrich future generations of stars and planetary systems. The remnants of supernovae become the raw material for new stars and planets. Like cosmic phoenixes, new stars rise from the ashes of their predecessors. These stellar explosions sow the seeds for countless others, enriching the cosmos with the building blocks of planets and life. A star's leftovers, setting the stage for our solar system. Imagine our Sun, a young star surrounded by a swirling disk of gas and dust, the remnants of a supernova. This disk contained the building blocks of planets, a cosmic soup of hydrogen, helium, and heavier elements. It was a dynamic environment shaped by gravity, rotation, and light from the nascent Sun. Think of it as a cosmic pizza dough being tossed and spun, gradually flattening into a disk. Within this disk, a process called accretion began, transforming gas and dust into planets. Dust grains collided and stuck together, growing into pebbles, boulders, and eventually planetesimals. Gradually, order emerged from chaos, forming the planets we know today. The dust bunnies of space, accretion, and the birth of planets. As planetesimals continued to collide and grow, the protoplanetary disk began to resemble a cosmic shooting gallery, with objects of all sizes whizzing around, their paths determined by gravity and chance encounters. Imagine a cosmic billiards game with planetesimals as the balls, their collisions shaping the destiny of the solar system. Closer to the Sun, where temperatures were higher, only rocky materials like iron, silicon, and oxygen could condense out of the swirling gas and dust. These materials formed the building blocks of the inner rocky planets, Mercury, Venus, Earth, and Mars. Further out beyond the frost line, where temperatures were low enough for ices to form, the gas giants, Jupiter, Saturn, Uranus, and Neptune, were born. These gas giants, behemoths of the solar system, grew to enormous sizes, their immense gravity attracting vast amounts of gas and dust. Jupiter, the largest planet, became a king among planets, its mass greater than all the other planets combined. Its gravitational influence sculpted the early solar system, flinging planetesimals inwards and outwards, shaping the orbits of its planetary siblings. The asteroid belt, a band of rocky debris between Mars and Jupiter, stands as a testament to the chaotic early days of the solar system. These asteroids, remnants of planetesimals that never quite managed to form a planet, serve as a cosmic time capsule, offering clues about the conditions and composition of the early solar system. Our cosmic cradle, Earth's formation and early evolution. Earth formed from planetesimals over millions of years, glowing red-hot and bombarded by asteroids and comets. A violent impact with Theia ejected debris that formed our moon. As Earth cooled, its surface solidified, forming the first crust and primordial atmosphere. Water vapor condensed, forming the first oceans. These events set the stage for billions of years of geological change and the emergence of life. The formation of the moon and oceans were just the beginning of Earth's fascinating story. A world in flux impacts, volcanoes, and the Hadean Earth. The Hadean Eon was marked by intense heat impacts and volcanic activity. The late heavy bombardment delivered water and volatile compounds, contributing to the formation of oceans and atmosphere. Volcanoes released gases, creating a greenhouse effect that kept Earth warm. This dynamic environment set the stage for the next chapter in Earth's story. The interplay of impacts, volcanic activity, and atmosphere paved the way for the emergence of life. A cooling embrace, the transition to the Archean. As the Hadean chaos subsided, Earth entered the Archean. The molten surface solidified, forming a thin crust. Early landmasses provided stable platforms for life to emerge. The atmosphere, rich in volcanic gases, created a greenhouse effect. Oceans formed from condensed water vapor and icy comets. The stage was set for the emergence of life in Earth's warm, chemically rich waters. The cradle of life, from primordial soup to single cells. The early Archean oceans were a dynamic environment where the building blocks of life formed, simple molecules assembled into complex structures like proteins and nucleic acids. These molecules began to cooperate, forming rudimentary metabolic cycles. Protocells emerged, capable of self-replication and passing on genetic information. Life, in its simplest form, had emerged, setting the stage for billions of years of evolution. Life proved to be tenacious and innovative. Early organisms relied on chemosynthesis, but a revolution was brewing. Photosynthetic organisms emerged, harnessing sunlight to produce oxygen. Oxygen reacted with iron in the oceans, forming iron oxide deposits. As photosynthesizers proliferated, oxygen began to accumulate in the atmosphere. This transformation set the stage for a dramatic change in Earth's biosphere. The rise of oxygen had a profound impact on life. The Great Oxygenation Event led to ecological upheaval and evolutionary innovation. Some organisms retreated to oxygen-deprived niches, while others adapted. Oxygen-based respiration allowed for larger and more complex organisms. The formation of the ozone layer protected life on land. The Great Oxygenation Event transformed Earth into a more hospitable planet. This paved the way for the evolution of complex oxygen-breathing organisms. The Proterozoic Eon was a time of profound change and innovation. Continents drifted, collided, and reshaped the globe. The atmosphere evolved, influenced by geological processes and life. Life flourished, with single-celled organisms evolving and thriving. Photosynthetic organisms spread, pumping oxygen into the atmosphere. The Proterozoic laid the groundwork for the explosion of life in the Phanerozoic. The dawn of complexity, from single cells to multicellular life. Single-celled organisms began to cooperate, forming colonies. These associations became specialized and integrated. Cells took on different roles, leading to greater complexity. Multicellular life allowed for larger organisms and new ecological niches. This transition marked a pivotal moment in Earth's history, paving the way for diverse life forms. Snowball Earth, a planetary deep freeze. Around 700 million years ago, Earth experienced a severe ice age. Glaciers extended to the equator, encasing the planet in ice. Life survived in isolated pockets of liquid water. The Snowball Earth event demonstrated life's resilience and adaptability. This extreme climate change set the stage for future evolutionary developments. The Cambrian explosion, life's grand diversification. Earth thawed, setting the stage for the Cambrian explosion. A burst of evolutionary innovation gave rise to major animal phyla. The oceans teemed with new life forms, transforming the marine environment. The Cambrian explosion marked a shift in the complexity and organization of life. This period showcased the power of evolution to generate diversity and complexity. From sea to land, life conquers the continents. For billions of years, life flourished in the oceans. The land remained a barren frontier. Yet life found a way. Imagine the first pioneers, algae or fungi, adapting to land. The transition was fraught with obstacles. Plants established a foothold on land. Their roots anchored them. Leaves captured sunlight. Plants transformed the landscape. Insects ventured onto land, followed by amphibians. The colonization of land was pivotal. The reign of giants, the age of dinosaurs. As continents drifted, life entered the Mesozoic era, the age of dinosaurs. Imagine a world with warmer temperatures, higher sea levels, and lush forests. Dinosaurs evolved and rose to dominance. From towering sauropods to fearsome theropods like Tyrannosaurus rex, dinosaurs occupied diverse ecological niches. Volcanic eruptions, asteroid impacts, and climate changes drove evolution and extinction. For over 160 million years, dinosaurs ruled the Earth. The Mesozoic era laid the groundwork for the rise of mammals and our own species. Cataclysm and renewal, the Chicxulub impact. Around 66 million years ago, a cataclysmic event brought the reign of the dinosaurs to an abrupt and dramatic end. An asteroid, estimated to be about 10 kilometers in diameter, slammed into Earth near the Yucatan Peninsula in present-day Mexico, releasing an unimaginable amount of energy, equivalent to billions of atomic bombs detonating simultaneously. Imagine the sky ablaze with fire as the asteroid, traveling at tens of thousands of kilometers per hour, ripped through the atmosphere. Upon impact, the asteroid vaporized, creating a crater over 180 kilometers in diameter and triggering earthquakes, tsunamis, and volcanic eruptions on a global scale. The impact ejected trillions of tons of molten rock and dust into the atmosphere, engulfing the planet in a shroud of darkness. The immediate aftermath of the impact was catastrophic. Wildfires raged across continents, ignited by the intense heat. Tsunamis, hundreds of meters high, inundated coastlines, reshaping continents. The dust and sulfur injected into the atmosphere blocked out the sun, plunging the planet into a prolonged period of darkness and cold. This impact, known as the Chicxulub impact, marked the end of the Cretaceous period and the beginning of the Paleogene period. It wiped out an estimated 76% of all plant and animal species on Earth, including the dinosaurs, bringing the Mesozoic era to a close and ushering in a new era, the Cenozoic, the age of mammals. Section 4, A Changing Planet, the Rise of Mammals and the Age of Ice. In the wake of the Chicxulub impact, Earth was a changed planet. The skies gradually cleared, but the climate remained unstable. The dinosaurs were gone, leaving behind a world ripe for the taking. Mammals, small and adaptable, survived and were poised to inherit the Earth. Imagine a world recovering from disaster, with new ecosystems emerging. Mammals diversified rapidly, evolving into a dazzling array of forms. Some, like the ancestors of whales and dolphins, returned to the sea, while others, like bats, took to the skies. The Cenozoic era was a time of dramatic climate change. The arrangement of land masses and ocean currents influenced global weather patterns. Around 2.6 million years ago, Earth entered a period of recurring glacial cycles, with vast ice sheets advancing and retreating across the northern hemisphere. These glacial cycles, known as the Quaternary Ice Age, had a profound impact on life on Earth, shaping landscapes, driving evolution, and influencing the distribution of plant and animal species. It was during this time, amidst the challenges and opportunities of a changing world, that our own species, Homo sapiens, evolved in Africa, our ancestors adapting to the demands of a planet in constant flux. Section 1. A planet transformed Earth's enduring legacy. From its fiery birth to a life-sustaining home, Earth's story is cosmic evolution, sculpted by gravity, volcanoes, tectonic plates, wind and water, and life itself. Continents drift like puzzle pieces, telling tales of ancient collisions. Mountains stand as monuments to immense forces. Fossils reveal life's evolution from single-celled organisms to diverse life. Oceans cover 70% of Earth, holding vast reserves of liquid water, regulating climate and weather. Oceans play a vital role in the carbon cycle. Earth's atmosphere, a delicate shroud of gases, protects us from space radiation, regulates climate and provides oxygen. Our atmosphere is shaped by geological and biological processes. Section 2. Our cosmic oasis, the fragile miracle of life. Amidst the vastness of space, Earth stands out as a beacon of life, a rare and precious oasis in the cosmic desert. The emergence and persistence of life on our planet is a testament to the extraordinary confluence of factors. A stable star, a suitable distance from the sun, a protective atmosphere, liquid water, and a dynamic geological environment. Life, once a tenuous flicker in the primordial soup, has transformed our planet, shaping its atmosphere, sculpting its landscapes, and creating a web of interconnected ecosystems of breathtaking complexity and beauty. From the towering rainforests of the tropics to the icy plains of the poles, from the depths of the oceans to the heights of the Himalayas, life thrives in a dazzling array of forms, each adapted to its unique environment. The very air we breathe is a testament to life's transformative power, its oxygen content a byproduct of billions of years of photosynthesis. The fossil fuels we rely on for energy are the remnants of ancient life, their carbon atoms once part of living organisms. Yet, for all its resilience and adaptability, life on Earth is also fragile, vulnerable to both natural and human-induced changes. The history of life on our planet is punctuated by periods of mass extinction, stark reminders that even the most successful species can be wiped out by catastrophic events or gradual environmental shifts. Section 3. A future uncertain stewardship of our pale blue dot. As we gaze out at Earth from space, a swirling blue and green sphere, we are reminded of its beauty, fragility, and uniqueness. Our planet, a pale blue dot, is the only home we know. The choices we make today will determine the fate of our planet. We have the power to be both destroyers and stewards. Let us choose wisely. For the sake of all life, the future of Earth is in our hands.